It is my pleasure to kick off the summer session of our seminar. We have some great speakers lined up, but also during the summer, due to some cancellations, we have a couple of free slots as well. So we extend our call for speakers. So if you know someone or if you would like to give a talk yourself, please let us know. And so today, for the first talk of the summer, we have a tandem talk consisting of two parts. We have Austin Anderson and Alex White from FSU, who will tell us about asymptotics of best packing and best covering. And as usual, this is a reminder that there'll be some time after the talk to socialize and maybe discuss the talk itself. So Alex, I think you want to go first. So please, floor is yours.
Yes, thank you, Alex. And before I begin, I want to thank Alex for the opportunity to allow myself and Austin to speak today. This is a joint work between myself, Austin, Alex, and Alexander Reznikov. So this is all a big collaborative effort that we've been working on for a good bit now. So I want to thank him for giving us the opportunity to speak on this. So to give us a quick intro, I'll be doing sort of the introduction on a result that I was sort of spearheading, and then give a quick transition to Austin to talk about some of the results from this. And so as Alex said, our title of this talk is Asymptotics of Best Packing and Best Covering. Okay, let's see, can I get, there we go. All right, so begin with a statement of the problem. So we have two problems to think about. Given a compact set, what is the maximum number of disks which can be packed into the set, which could be called the best packing problem. And similarly, there's the dual problem, which asks, what is the minimal number of disks needed to cover a given compact set? And this is the best covering problem. So some examples to think about how this problem can be applied in certain cases would be, imagine we have a gas that's fitting a container. So how will the gas expand to fit that container? How will the particles of the gas expand out and interact with each other to fill that container? And then secondly, let's imagine we have an important resource that we need to distribute over a large area with irregular shape. What's the best way to place that resource over a large area? So I could imagine there's all this talk about electric vehicles recently, and there's this issue of where should the charging stations for these electric vehicles be split over a large area, let's say the continental United States. So then there's an idea that, okay, one charging station should serve a certain area, let's say like a given radius, and then we want to make sure that these charging stations and their servicing areas should equally cover the entire United States while not having too many people rely on a single one. So there's an idea of trying to best cover without having too many people in a given area relying on one and not enough people relying on another. So there's a sort of additional weight you can tie to this sort of question. Okay, so I have this first example to sort of demonstrate what a best packing can look like and what a poor packing can look like. So I have two squares on the left and on the right where I've placed 4 points. So I've placed 4 points in the 4 quadrants of the square. So 1, 2, 3, 4. And then with these 4 points, I've drawn the disks of equal size which cover this given square. And I've placed these 4 points in such a way that this pretty well covers this square. So these disks are the minimal size disks needed to cover this square. And then on the right, we can see a contrasting example of when this is poorly covered. So what I've done is I've taken these 4 points from the 4 quadrants and I've moved them closer towards the center of the square. Now, because I moved these 4 points closer to the center of the square, that means the 4 corners of the square are further away from each of the 4 points. So that means the radius of the disk needed to cover the square has now increased because I've increased the distance from one of the furthest points, the corners, from the remaining 4 points. So this sort of illustrates one of the key ideas behind covering, being that as you move points around, this can affect your covering depending on where the farthest points are from your given set away from your configuration that you're using to cover. Okay, so I want to start by getting out some of the definitions and formalities behind packings and coverings, and then sort of talk about how these problems are related to energy. So let's start by defining the best packing, and then I'll move on to best covering, and Austin will talk a little bit more about the best packings later on. So we always assume RP is our ambient space, and we take a n-point collection of points, call it omega n, inside of our ambient space. So this is our configuration. Then for the best packing distance, we start by defining the minimum distance between any distinct pair of points as delta of omega n, and that's just the minimum between any distinct pair of points. Then the best packing distance is defined as the supremum of all those delta omega n's over any collection omega n contained in a compact infinite set A, where our configuration has to be exactly n points. So this is the exact best packing distance on your compact infinite set A of n points. So below I have this example where the best packing of n points on our unit interval 0 to 1 consists of n equally spaced points with separation 1 over n minus 1. So I have an example of 5 points equally spaced out on the unit interval. So the space between any two pairs of points is at least a quarter. So we can see how this is sort of well separated, and there's a nice picture to it. There's a nice geometry, how they're all equally spaced. And on the right, we can see an example where it's poorly separated, where we have this cluster of points really close together and all of this extra space to the left and to the right where we could have spaced them out better. So we have the optimal versus the suboptimal case. Okay, and then we'll contrast this with our covering example. So our best covering, we again take an infinite compact set and define the best constrained covering distance of endpoints to be taken as you look at points y in your set A, and you look at the distance from y to each of your points in your configuration, and you can define this distance to be the distance between y and its nearest point of the configuration. Then you want to find what's the furthest point away from all points of your configuration. And then we want to minimize that distance of the furthest point from your configuration by changing configurations contained in the set A. And I've highlighted this argument here because this is what makes it a constrained covering, where we restrict the configuration of covering points to be contained inside of the set A. So then this eta n of A is your best constrained covering distance. Then contrast this with the unconstrained covering, where we take omega n star, and we take that collection of points in the ambient space RP. And we just denote all this with the star in the addition to our notation. So again, we have the distance from y now to the unconstrained configuration omega n star. Find that distance of y to its nearest point of the configuration. Find the maximum y in A so that y is the furthest point away from that configuration. Then minimize over configurations in the ambient space so that you find the configuration which best covers by minimizing the distance from all points of A. Okay, so best packing and best covering can also be viewed as limiting cases of the following: of minimal energy and polarization. So to give a brief description on the minimal energy, if we have a lower semi-continuous kernel, taking the Cartesian product of our set and then map it into the real numbers, and we extend it up to infinity, the configuration omega n, as seen previously, we take n points. And for this to be well defined, I think we need omega n to be distinct points. Then its K energy just is given as the sum of these kernels of these distinct points xi and xj. So an example of kernel that you could think of would be the inverse distance. So 1 divided by the distance from xi to xj. So as xi and xj get closer to each other, that contributes a very large amount to your overall energy. If Xi and Xj are very far, then you're not contributing too much to the overall energy. And then by minimizing overall configurations contained in your set A, you obtain the minimal K energy. Now, it's worth noting that finding the exact optimal configuration that minimizes your energy is in general a difficult problem. And Austin can talk a little bit more about some of the results that have recently been achieved in this direction, but in general, this is a very difficult problem to approach. And so this is one of the main motivations as to why we want to think about coverings and packings, is because coverings and packings are limiting cases of energy and polarization, and they're at least a little bit easier to work with. And I'll try to give a good idea of why that's the case. Okay, along with energy, we have maximal polarization, where the problem of maximum polarization is defined similarly, where we're taking these sums of kernels, where instead of looking at distinct pairs of points of the configuration, you take a point Y in your set over which you're finding the polarization, and then you're looking at the sums of these kernels from Y to your points Xi in your configuration. Then you can consider this minimum of these UKs, and that gives you your polarization for your set A over a given configuration omega n. And then the nth K polarization, and then we have in parentheses Chebyshev, because this has some relations to the Chebyshev polynomial. This kth polarization constant of A is just defined as the supremum over all configurations omega n inside A of these infimums of these sums. So again, this is sort of a difficult problem to get a good handle on, and that's why we want to try and move these questions that we have about energy and polarization into the cases of packing and covering. So this moves into our current work. What's the goal? So we have these questions and results that we'd like to have for polarization, or questions that we have about polarization that we're not quite sure how to approach. And we want to take these known questions and sort of try to translate them into coverings. So the way that we do that is we take results that have been known or recently proven by polarization and try and apply these results to coverings to see if we can get similar or analogous results. And that's what I'll be talking about, is our recent results, which sort of corroborate that this can be done, is that we can take polarization and apply these to coverings. And this shouldn't be too surprising, because coverings are known to be limiting cases of polarization and energy. So we're optimistic that we would be able to get these analogous results, and in fact we have. Now the new current direction is, okay, so we're starting to get these new results for covering. We can hope that now we can start to push these to get even newer results of stuff that isn't known for covering, that will then hopefully lead back to new results that have been recently more difficult to show for polarization. So the general pattern is, let's take stuff to the easier case. Let's see if we can use the fact that coverings are a little bit easier to work with to try and get some new results, and then hopefully we can reapply those back to polarization. Okay, so now let's get on to the main theorem that I have to talk about. So this is the main theorem, and this is analogous to what was shown previously for polarization, with just some slight modifications. For compact sets A in our ambient space and integers D and P, such that 1 is less or equal to D, less than or equal to P, and P is at least 2, then if the Hausdorff D measure of A is positive, then if the limit of our unconstrained covering, and if we multiply by this factor of n to the 1 over D, this is the growth factor, if this limit overall exists, then the limit for the constrained covering, also multiplied by this factor of n to the 1 over D, also exists, and they agree. So there's a little bit of simplifications that we were able to do, because covering is not reliant upon some extra factors. So going back to polarization, you can define these kernels to be dependent on a parameter S. Then this theorem was stated where you had to keep track of what happens with that parameter S as it either goes to 0, or if it goes to infinity, what happens with that relative to these other parameters D and P. But because covering is not reliant on that in any way, we're able to drop sort of some of the conditions that were reliant on that parameter S. Now, without getting into the details of this theorem, I wanted to present the two main ideas behind this theorem, which were present in two of the lemmas that we used. And this should hopefully give a good idea as to why covering is so much better to work with. Okay, so our first lemma, we titled it similarly to an analogous result for polarization, is weak separations. So this lemma is essentially encapsulated by this cute little drawing that I have. So what I have is I have a set which is compact. It's the interval from 0 to 2 and the point at 3. So I've taken this set and I've covered it by exactly 2 points, the point x0 and the point x1. And the covering radius for this configuration is exactly 1, because from x0, it takes exactly radius 1 to get to 0. And then from x1 at the point 2, it takes radius 1 to get over to the point 3. Now, what this lemma essentially gives us is a little bit of flexibility in the covering points, because if I take the point x1, and if instead I move it over to the point 3, which can be seen in this second image, so all I've done is I've moved it from 2 to the point 3. I achieve the same covering radius by changing this configuration. So I have not had to increase my covering radius at all because of some of the properties of this particular set A. So depending on the set A that we're looking at, we have some degree of flexibility with how we can arrange our covering. So if I have a problem with, I have these points x0 and x1, and if I don't like they're too close and that there's a little too much overlap in the covering, then I have a little bit of flexibility where I can move x1 a little bit further apart and still cover the same set. So that was the heart of the content of this first lemma of weak separation, that coverings are a little bit more flexible, where I can move points apart, and that might not necessarily affect the covering radius. We do have to be a little bit careful, but it's not the same story with packings and energy and polarization, because or at least with packings and energy, because packings and energy are directly computed by the difference in the distance between these points. So moving them will absolutely affect packings and coverings, or sorry, packings and energy, but coverings offers a little bit more degree of flexibility. And so this was very advantageous for the proof of this theorem, and then is in general why we're optimistic about why coverings are a little bit more useful. And then the second main lemma, which was necessary in order to proceed with the theorem, which was to take an unconstrained configuration, and we want to replace it with constrained points. So I have in this first image, I have a set, which I haven't shown all of it, but I have these points which lead up to 0, and then I have the point at 0, and then I have the point at 2, and then it continues off a little bit to the right of 2. And this is just a zoomed in picture where I have a particular unconstrained point, xi star. And xi star is lying outside of the set because it's an unconstrained point. Now, in the direction of the proof, part of what I want is I want to make sure that I can move these points that are outside of the set and try to move it closer to being inside of the set so that it becomes no longer an unconstrained configuration. Now, the idea behind this is I want to look at where does this unconstrained point cover the set. So in this example, it's covering the point at 0 and it's covering the point at 2. So in order to ensure that I'm covering the point at 0 and 2, I needed to add 2 points in order to replace this one unconstrained point. So I add the point x1 at the point 0, and then I give it the same covering radius. So I get x1 with the covering radius of 1 at 0, and I replace x star intersecting at the point 2 with the point x2 centered at 2, and I give it the same covering radius. So by this replacement of 2 additional points, I'm still able to cover the points 0 and 2 with 2 new points, x1 and x2. And the key takeaway from this lemma is that this can be done without adding too many extra points, x1 and x2, and that this is actually dependent on the Kissing number in dimension D. So depending on the dimension that you're looking at and the Kissing number for that particular dimension, that's what can be done. So I think in this example, I have this for dimension 1. So the Kissing number for dimension 1 is 2. So I had to replace x star with at most 2 points. And why this is okay is that in the proof of our theorem, we are doing the asymptotics as the number of points goes off to infinity. So since I'm already increasing into infinity, as long as I can ensure that the replacement of these unconstrained points with constrained points doesn't lead to a significant increase in the number of overall points, since I'm taking the number of overall points to infinity anyways, then this is okay to do. And that this is part of the essential idea of what we need in order to proceed with the theorem. So then these two lemmas also give us a corollary, which is also similar to what happens with polarization, where depending on your set A, you can guarantee that not too many points of your unconstrained covering, xi star, will lie very far away from the set A. So this xi star is fairly close to the set. It's only radius 1 away. So then I can pretty quickly replace it with 2 points. And then our secondary result was that we can guarantee that there's a number dependent on some extra parameters and the set itself. You can guarantee that not too many of these points are going to show up. And that again allows us to proceed with the limiting argument. Okay, so that's the main two lemmas that I wanted to talk about. And then that was the heart behind the theorem itself. And now this theorem and its contrapositive has some interesting results worth discussing. So I'll just go back to the theorem for a second. So the theorem was the statement that if the limit for the unconstrained covering exists, then we're guaranteed that the limit for the constrained covering also exists, and they agree. Now, Austin will take it up from this transition slide and talk about how the contrapositive of this theorem has some interesting results on the stuff that he's been doing. So I'll stop sharing and allow Austin to take over.
Okay, thank you, Alex. Go ahead and share my screen now. So before I begin, I'd also like to thank the organizers so much for giving me and Alex the opportunity to talk here today. And I'd also like to thank Alex, Olex, and Sasha for all of the really engaging conversations we've had about these particular problems over the past, it's going on a couple of years, I'd say at this point. So to begin my part of the talk, I'm actually going to take a slight detour into the densest sphere packing problem in RP, because these quantities will show up later on when we go on to discuss the asymptotics of packing and covering. So what is this densest sphere packing problem? It asks, what is the densest arrangement of congruent p-dimensional spheres that you can place without overlapping in RP? And of course, you have to be more rigorous with this notion of density when you're filling up all of Euclidean space. So what we mean by this is the proportion of the volume in that ambient space that the spheres occupy. So for the remainder of the talk, we'll denote this by delta P. Now, this is just a famously challenging problem that so many people have tackled in the past. And despite all of this effort, up until 2015, only the cases P equals 1, 2, and 3 were known. And even before that, in 2005 was when the case P equals 3 was finally settled by Thomas Hale, and this was known as Kepler's conjecture. So really, there's been a lot of fascinating progress on these problems only just recently. And two of the most recent results are for dimensions P equals 8 and 24, resolved by Marina Wiazowska and Henry Cohn, plus their collaborators. So amazingly, they were able to show that E8 attains the densest sphere packing ratio in R8, And the Leech lattice attains the densest packing in R24, where by this we mean you're stationing the spheres so that their centers are on these points of the lattice. So this is very interesting because they really had to exploit a lot of the hypersymmetry that you see in these lattices. And it's very interesting that they were able to do this in higher dimensions where we still have this lack of understanding in, basically every other dimension. So before I continue, we can also always mention the case for dimension 2 is the hexagonal lattice, where you pack your circles in R2 so that their centers are on the vertices of the hexagonal lattice. So this shows that our friends the honeybees have some intuition about best packing. Oops. Okay. So to make the growth order of packing and covering more intuitive, I just wanted to recap it briefly. So why do we consider the asymptotics of packing and covering? As Alex said, it's because proving exact answers for these problems is generally very hard, even for a very small number of points. And even if you're looking at highly regular sets, such as the sphere, I know for the related problem of minimal energy on the sphere, there are many famous open problems. You have Smale's seventh problem, Thomson's problem, which, respectively ask for some nice algorithm for distributing minimal energy points on the sphere and then just finding these points at all. And, exact minimal energy configurations, at least, are only known for a few given values of n for energy. And because this is related to packing, it means that packing is also hard. And similarly, the dual problem of covering is hard. So what this means is we need to consider large n if we're going to have any hope of understanding somehow how these things behave for a large number of points. So to that end, if we let D be the Hausdorff dimension of a compact set contained in RP, then it turns out that the growth order, or you could maybe consider it a decay order, of the best packing of endpoints on A, the best constrained covering of endpoints on A, and the best unconstrained covering of endpoints on A listed consecutively here, they all have the same order, which is n to the minus 1 over d, as the number of points grows very large. So this highlights the duality between best packing and best covering that we like to talk about a lot as we try to come up with new results for best covering. And so to make this idea of the dependence on dimension a little more intuitive, if you consider just a line segment of length L living in R1, then the minimal number, the minimal radius necessary to cover this line segment by n points, by spheres, n spheres centered at points on this line segment is L divided by 2n. So for instance, for the 5 circles that we have below, you could see the radius that we need is L over 10 to cover. And clearly this is order n to the minus 1 over d in this case, because the Hausdorff dimension of a line segment is 1. Now, sort of the main goal of asymptotics of best packing and best covering and minimal energy and maximal polarization is to try to take the most mild smoothness assumptions that you can make on your compact set A and translate this into existence of asymptotics for these various quantities. So today we're primarily focusing on best packing and best covering, but it's worth mentioning that a lot of the most robust progress on this was initially done for minimal energy. So this type of theorem is generally called the poppy seed bagel theorem now due to these minimal energy problems, and we'll briefly see why. But first, I want to state the poppy seed bagel theorem for best packing. So for our first version, we're going to let A just be a smooth D manifold embedded in RP. We'll let HD denote the D-dimensional Hausdorff measure, which is in this case, if we're looking, specifically on this this smooth D manifold, then it's just the surface measure for A in this case. Then we have, not only does the following limit exist, but the limit as n goes to infinity of the best packing radius of n points on A times n to the 1 over D is equal to a positive constant C sub D, depending only on D, times the Hausdorff measure of A raised to the 1 over D. So that tells us about the existence of this limit, but furthermore, and this is where we'll see poppy seed bagel comes into play, we can discuss the distribution of the best packing configurations. So as long as your set has positive Hausdorff measure, then if you begin with a best packing configuration omega n, and you form what we call an empirical counting measure nu n by being 1 over n times the sum from 1 to n of delta xi. This is just placing a point mass of 1 over n at each of the points xi in your best packing configuration. Then it turns out that these configurations are uniformly distributed with respect to normalized Hausdorff measure as n gets very large. So a mathematical way of saying this is that in the weak star topology of probability measures on A, these measures, these empirical counting measures, nu n, converge weak star to the normalized Hausdorff measure as the number of points gets very large. So, there's recently been an entire text called Discrete Energy on Rectifiable Sets, and it's really this idea of discretizing manifolds via these optimal configurations. So we see that this happens for packing, which is nice. I've no doubt mentioned the name of the theorem, poppy seed bagel theorem, several times at this point. So for anybody who has not seen this before, the reason why it's called the poppy seed bagel theorem is because if we consider a particular smooth manifold being the torus in R3, which as we know has Hausdorff dimension 2, then the result says because the best packing configurations are uniformly distributed for large n over the surface of our torus, if you think of these points in the best packing configuration as being poppy seeds, it's like the poppy seeds are being uniformly distributed over the bagel as the number of points gets very large. Now, relating back to the first slide of my part of the presentation, we actually know a formula for this constant C sub D that we get from the asymptote for best packing, and it is the largest density sphere packing value in dimension D divided by the volume of the unit ball in RD, all raised to the 1 over D. So what this means, formulaically is that we really only know this C sub D explicitly for D is equal to 1, 2, 3, 8, and 24 at this point. Okay, so we've discussed the poppy seed bagel theorem for best packing, and we'd like to know what is known, in the way of these kinds of theorems for covering. So to my knowledge and my collaborators' knowledge, the most general form of this poppy seed bagel theorem that we have for covering was actually done decades ago by Kolmogorov and Tikhomirov, and it was only proven for Jordan measurable sets in the unconstrained covering case for full dimension and nothing about distribution. So you have the part one in this sort of very restrained case, and you don't have anything about distribution. So stating this more rigorously, we'll call it the poppy seed bagel theorem for unconstrained covering for the rest of the talk. If A is a subset of RP that is compact, and the condition for Jordan measurability being that the Lebesgue measure of the boundary is 0, we can define this quantity sigma p star as the infimum over n greater than or equal to 1 of the best unconstrained covering radius of endpoints on the unit cube in RP. In this case, we find that this constant sigma p star is positive, and the limit as n goes to infinity of the best unconstrained covering of endpoints on A times n to the 1 over p is equal to sigma p star times the Lebesgue measure of A raised to the 1 over p, or the volume. So note the proportionality with Lebesgue measure in this case raised to the 1 over p. So this is mimicking what we saw for Hausdorff measure in the poppy seed bagel theorem for best packing. Now, one of the first corollaries of Alex's theorem that he mentioned just before we turned over is we can take this theorem due to Kolmogorov and Tikhomirov, and we immediately get a similar theorem for constrained covering. So because existence of unconstrained covering asymptotics now implies existence of constrained covering asymptotics, and we know that the limits agree in this case, then we get a poppy seed bagel theorem for constrained covering, at least part one in this very limited case. So if A, again, is a compact subset of RP, where the Lebesgue measure of the boundary is 0, then the limit as n goes to infinity of the best constrained covering of endpoints on A times n to the 1 over p is again sigma p star times the Lebesgue measure of A raised to the 1 over p. So to my knowledge, this is all that's known, and this is the most general poppy seed bagel theorem that we have for unconstrained and constrained covering at this point. And it's really worth harping on that we have a much more general poppy seed bagel theorem for packing and even for minimal energy with very mild smoothness assumptions. So not even the most mild assumption is that if you assume A is just the image of a compact set under a Lipschitz map, then you get exactly the same sort of results. And we really hope in the future, perhaps using Alex's mode of thinking about, coming up with more about covering, that we should be able to adapt perhaps some of these ideas about packing to the covering scenario, or use some of his ideas to get more general results for covering. Okay, so now that we've discussed the poppy seed bagel theorem and when we get existence of these asymptotes, it's a very natural question to ask, how much regularity do you ultimately need to guarantee existence? And is there some sort of sharp result that we can show where you don't get existence of the limits if you don't have regularity? So, so a typical class of very non-smooth sets that's often considered in analysis, of course, is the fractals. So what we'll do is we'll begin, and this was the method or the approach taken by past researchers when thinking about the sharpness of these results, is we'll examine packing on the 1/3 Cantor set. Now, the interesting thing that we'll come to find out from this analysis is that there is some hope of finding some subsequential limits for these best packing and best covering and even minimal energy and polarization problems on fractals. So beyond just non-existence, there's going to be some interesting array of results that you can prove for these geometric questions on fractals as well. So moving on, we have a short picture depicting a well-behaved subsequence of points under best packing on the 1/3 Cantor set. So of course, the diagram here is we start out with the interval 0 to 1, we remove the middle third, and on each of the remaining line segments, we remove their middle thirds, and we continue this process iteratively to get the Cantor set. Now, the reason that the sequence of 2 to the n points works out so well is it's this maximal indexed best packing configuration. So what we see is that with 2 to the 1 points, we can put the 2 points on the extremal ends of the Cantor set, 0 and 1. And when we move up and we increase the exponent by 1, the result on the best packings is that we just scale and translate these into the leaves of the Cantor set. So we end up with a configuration of 4 points, of course, with the points being at 0, 1/3, 2/3, and 1. And what we see is that the best packing continues on in this way, where you scale and translate into, smaller and smaller leaves, where you take on a factor of 1/3 at each increase in the exponent. So from this, we find that the best packing of 2 to the n points on the Cantor set can be explicitly found, and it is 1 over 3 to the n minus 1 when n is greater than or equal to, n is greater than or equal to 1. And because of this, and because we know the Hausdorff dimension of the Cantor set is log base 3 of 2, then the calculation of the asymptote reveals, taking into account that 2 to the n raised to the 1 over d gives us 3 to the n, the limit, it converges and it's just equal to 3. So we get that the limit at least exists along a subsequence. And the way that we show that the poppy seed bagel theorem, or at least the existence of this asymptote, ultimately breaks down for packing on the Cantor set is by considering a second subsequence where we add 1 extra point to each of those 2 to the n point configurations. And essentially a pigeonhole argument reveals that you can't introduce an extra point at any of these iterations without multiplying the best packing by a factor of 1/3. So you scale it down by an entire jump of 1/3 every time you add that additional point, although asymptotically 2 to the n plus 1 and 2 to the n are indistinguishable. So what this tells us then is that we get a separation between the lim sup and the lim inf in this case. So the limit overall does not exist. And so the question becomes, what else can we say on more general fractals? And can we say sort of similar results for covering? So to do this, we're going to want to define a suitable class of fractals to work on. So to that end, we're going to call our fractals self-similar fractals, and we define them as follows. A compact set A contained in RP it's basically going to be the unique attractor of a set of K similitudes. And by similitudes, we just mean these mappings psi j, which are contraction mappings satisfying the formula psi j of x is equal to rj times O of x plus zj, where O is an orthogonal matrix in p dimensions allowing for rotations. The rj is scaling the individual leaves downwards, and zj allows for translations. Additionally, we assume that our self-similar fractals for our analysis also satisfy the open set condition, which on its own would guarantee that the Hausdorff measure of the intersections of these leaves is 0, but we assume a stronger version where the leaves are disjoint to simplify the analysis. So one example of a self-similar fractal, which is not just the Cantor set, could be the Cantor dust in the unit cube. So this would have 8 similitudes, I believe, all with contraction ratios of 1/3. Now, there's sort of a bifurcation in the analysis between the dependent and the independent case. So what do I mean by this? For a self-similar fractal A with similitudes psi j and contraction ratios corresponding to those rj, we say that the similitudes or the fractal are dependent if there exists some positive h, such that the set of linear combinations over the integers of the logs of these contraction ratios is the lattice hz for that h. And if this condition is not satisfied, we say that the similitudes are independent. So, obviously only one of these can be true. So that's why we get the two different ones. And so for example, the 1/3 Cantor set is a dependent self-similar fractal because its similitudes, you can find them are 1/3 x and 1/3 x plus 2/3. An example of one that would be independent would be something, for instance, where the contraction ratios are 1/3 and 1/2. Okay, so finally, we'll get into sort of the most robust poppy seed bagel theorem that's currently known for packing and covering, at least barring one more thing that I'll mention in a couple slides. So to state this result, first I want to introduce two distribution functions. So for a positive epsilon, we'll define n of epsilon as the maximum cardinality of a best packing configuration of n points, which has separation greater than or equal to epsilon. And sort of conversely, we define m of epsilon as the minimum cardinality of a best covering configuration, which has covering radius less than or equal to epsilon. So in view of these two distribution functions, we have that a self-similar fractal of Hausdorff dimension, if we're considering a self-similar fractal with Hausdorff dimension d, then the following limits, so our usual best packing asymptote and the limit as epsilon goes to 0 from above of epsilon times this distribution function raised to the 1/d, and the analogous covering limits, these each exist if and only if the similitudes to finding A are independent. So if these similitudes are independent, we get each of these limits exists and they're equal. And if what I mean by equal is line by line. And if they are dependent, then the limits will not exist. So a brief sketch of this proof is that the first direction, independent gives existence, was due to Stephen P. Lally, and he used renewal theory from probability, which is shown to be a pretty fruitful theory for a lot of these problems recently, actually. And the dependent case implies non-existence, goes as follows. If your fractal is dependent, then you're going to be able to find some r in between 0 and 1, and the contractions will look like r raised to the ij, where these ij's are relatively prime positive integers. And after you have this, some recurrence will occur, and using the fact that the best packing of n of Rn points is greater than or equal to Rn and a short lemma, which shows that the best packing, when you add 1 point to that previous subsequence, is less than or equal to a constant times r to the n for some c less than 1, then you're essentially able to apply the same line of reasoning as we did for the Cantor set to these general dependent fractals. And the dual problem for constrained covering, you basically just replace n of Rn by m of Rn, and instead of adding a point, you subtract a point and you flip the inequalities, and your c now, instead of being less than 1, is some d greater than 1. So, the duality between these two quantities really helped a lot in developing the proof for the constrained covering case. Now, the final result that I want to state, which is in fact a second corollary of Alex's proof from earlier, will go as follows. If we now let m star of epsilon just be almost the same as m of epsilon, but for unconstrained covering, then by taking the contrapositive of his result, we immediately get the following theorem. If A is a dependent self-similar fractal with Hausdorff dimension D, then each of the following limits do not exist. The limit as m goes to infinity of the unconstrained best covering radius of m points on A times m to the 1 over D, and this limit as epsilon goes to 0 from above of epsilon times m star of epsilon raised to the 1 over D. So I believe, you know, you would, I think the lim sup and the lim imp of these two quantities, or lim sups of these two quantities would agree, but ultimately they're separated. So yes, so we have two very nice corollaries of his result from earlier. And that's all that I have for today. Here are some of our sources. We've accumulated several of them over the course of this work. Thank you, everybody.
All right. Thank you, Alex and Austin, for the nice double talk, which had results for a good pair of talks, I think. So let me open the floor for questions, comments.
I do have questions. I just wanted to let anyone else go first. Okay. Well, if no one else has questions right away, then yeah, I'll start that off. I maybe missed it, whether or not you said it, but so there was a poppy seed bagel theorem for best packing.
Mm-hmm.
I was unaware of this. Is that a result that you two have made, or is that a result of someone else's?
It's Baratychov, I think, maybe circa 2015.
Okay.
Yeah, so you want to look at asymptotics of best packing on rectifiable sets. So,
Okay. So
yeah.
that's good to know. Okay, so you have so right there at the end of the talk, you had this result where about limits existing or non-existing.
Mm-hmm.
So if you have dependent if darn it, what is it called? But if you're in the dependent setting, then you know that the limits don't exist, but you did show that for the Cantor set, the limit exists for some subsequence.
Yeah.
Do you know if, regardless of whether or not you're in the dependent or independent case, as long as you have self-similar fractals, do you always have a subsequence for which you have convergence to a limit?
Yes, that's let me think. Yes, you do. Yeah. So from Lally, you actually know this. Yes. So he has in his paper the packing and covering functions of some self-similar fractals. He shows that in the dependent case, you have convergence along various subsequences for packing and constrained covering. One interesting thing, though, is that he doesn't say anything about unconstrained covering. So, you know, we do know that existence of unconstrained implies existence of constrained, but we don't know the reverse. And in fact, you know, there might be some intuition to think that that's not necessarily the case. So, so what we can say is that, yes, it is resolved for constrained covering and best packing. You do get convergence along some subsequences, even in the dependent case.
Okay. Okay. So yeah. So some of these results, right? They're around for what, like various types of rectifiable sets, things of various different dimensions. Do your results for self-similar fractals then also give information about sets that were also previously unknown? Like, you know, if you know something about a self-similar fractal, maybe you know something about certain sets that those kind of fractals are embedded in.
So I think that honestly, Olex might know more about this, but some results which have been done for convergence along a minimizing sequence. So, you know, a subsequence obtaining the lim inf sort of incorporate this idea of like, if you have a subset of a self-similar fractal, then you get some corresponding formula, which looks a lot like, you know, the original Poppy-Seed-Bagel theorem, but it takes into account that you're looking now at the volume of the embedded subset instead of the overall. So.
Okay.
Yeah.
Okay. And so not knowing how new these results are, but understanding what you were saying about the connection, have you all had the opportunity to look into seeing if this helps you better understand polarization on fractals or other sets? Have you had the opportunity to look into that?
Yeah, we've recently considered this problem, and we do hope to put out some work on that soon, actually.
So it's been positive. Something has come out of that.
You know, I didn't work as heavily on this particular problem, so I don't know if I feel as comfortable saying that it's resolved, but.
Well, I didn't ask about that. Just I was asking if it had indeed led to some positive results.
Yeah, so we do have some nice results for polarization on fractals, and also for minimal energy, of course, on fractals. This is there's been a lot of that recently, and the title of a paper that I just put on arXiv with Sasha is just minimal Riesz energy on balanced fractal sets, which takes some results that were only known for dependent fractals where all of the contraction ratios are the same, and it upgrades those to the case where maybe they're not the same, right? So you could have a dependent fractal with contractions r squared, r cubed, r to the fourth, for instance, and you can get, for instance, convergence of the minimal energy along some nice subsequences.
And another question. Actually, I guess I'll pause here. If anyone else has questions, I can stop for a moment.
One quick question. With in the case of integral dimensions, the one consequence of the packing Poppy-Seed-Bagel theorem is this universality result that the limit for packing depends only on the Euclidean packing density and the Hausdorff dimension of the space you're packing in. And in a case where the limit exists, so you've got one of these self-similar fractals with independent similitudes, do you get any sort of independence like this?
Yeah,
I don't know if you have counterexamples or.
It's a very interesting question. Yeah, I've sort of tried to, I haven't thought about it as much. It's not a very well-formed thought, but I have been interested in if there's some way to better understand like the value of these asymptotes in a more geometric way as we do for sets with regularity, as you're talking about.
Yeah, I think it would be fascinating either way. If you don't get universality, that would be great to know. If you do, then it would give at least a sort of plausible definition of what the sphere packing constant should be in a fractional dimension, which would be great.
That's an interesting direction that we definitely would like to look at soon.
Sounds great.
So
I don't think we understand any relation to Euclidean spaces, right? So I guess what your question is, if I understand correctly, basically, okay, we know for integral dimensions it's related to these Euclidean packing problems. Yeah. What is the flat case for a fractal?
Exactly. So for example, if you look at a fractal where these limits exist, if you normalize the fractal to have Hausdorff dimension 1, then is the value of the limit determined purely by, to have Hausdorff measure 1, I mean, is the value of the limit determined purely by the dimension? I'm guessing it probably isn't, because I don't see any reason why it should be, but either way, it would be worth knowing.
Yeah, I don't want to say anything because I will probably lie if if I say something without thinking. Yeah, I don't think we can say right now that the constant is universal. Yep.
By the way, is your paper available somewhere? It didn't look like it was on the web yet.
That is correct. It is
It's-
not. Yeah.
It's still in writing.
Sounds good. I'd love to see a copy when it reaches the point where you're interested in feedback from people.
Absolutely.
I had a question about something that was said on one of the slides about what was it? It was if it was in the dependent setting, you could find an R between 0 and 1 where you could take powers of R that were prime powers. And-
that was, it's where those powers are relatively prime. So it's basically, if you have 1/4 and 1/16, then you could think about this as being a half squared and a half, a half raised to the fourth, I guess, maybe. Or,
But are
no,
the
in reverse? Sorry, yeah, I'm getting. I'm
no,
confused.
that's fine. But like, are all of these ratios rational? If you said that, I missed that.
Mm,
Because
Not-
if not, right, if it was just a bunch of irrational numbers, I'm confused about how that would happen.
mm. No, so the way that we get the relatively prime powers is it's basically you make a substitution if they're not relatively prime. That's the idea. So, if you're looking, it's this, here's a better way of stating it. If you have contraction ratios R squared and R to the fourth, make a substitution, capital R equals R squared, and then now you have.
Oh, no. That's not what my question is.
Oh.
My question is more of that. Maybe I'm just forgetting what it means for the ratios to be dependent, and maybe I'm just not remembering the definition correctly. But I guess, is it? So you were saying. Okay, could I see what the definition of
Yeah,
dependent is again? Because that might answer my question. So,
Here we go. Oops. So here's I'm still sharing. So here's the definition. So remember, we're taking linear combinations of the logs and we're only allowing the coefficients to be integers.
okay. So then, this seems like it would make more sense that you would get it. Okay, thanks. That was a really interesting talk. There was quite a bit of different things happening in it, and that was, this is very interesting. This is cool.
Thanks. Yeah, it's definitely there's been a lot of, stuff we've luckily been able to find out about these really weird sets and how they behave for these classical problems.
I guess, should I stop the recording?
Yeah, go ahead.
All right.